35. So this is case study as part of group 17 chemistry on the halogens. We want sodium chlorate 5. So the name itself, the chlorate, refers to chlorine with oxygen, just like sulfate, nitrate, phosphate. The 5 then, the V stand for chlorine plus 5. We are looking at ClO3 minus as well as Na plus. This is a case study. So -1 is the oxidation state of the ions. So chlorine plus 3 times -2, the oxidation state of each oxygen. Chlorine there is plus 5. I've used the charge of the anion to work out the oxidation state of the chlorine. If you decide to put in the sodium, they'll have a +1. The overall compound will have a 0 oxidation state. If you're talking about the overall compound, I'm using the ion here, so it's the exact same thing. This is part of the AS case study under the reaction called disproportionation as an AS redox topic, where a species is both oxidized and reduced in the same reactions. So looking through the options, option 2, we have CO2 plus NaOH, but this is cold and dilute, so this doesn't go all the way to chlorine plus 5. This actually stops at chlorine plus 1. This is sodium chlorate 1. And this is chlorine -1, chlorine +1, chlorine 0, and I simply need 2 NaOH to balance the equation. It stops here. It doesn't go all the way to chlorine plus 5 at all. So number 2 is wrong already. We're just looking at only 1 is correct. So therefore, option D. Okay. But looking at it, I mean, you should be able to balance the equations for option 1. These are hot concentrated NaOH. Let me just spell that properly. Hot concentrated NaOH. This is the extreme condition. So it goes all the way to chlorine plus 5. Here is where I'll use changes in oxidation number to help balance this equation. NaOH plus CO2, I still get NaCl. This is chlorine -1. I will get NaClO3. This is chlorine plus 5. And I'll get H2O. This is chlorine 0. Oops, chlorine 0. Using changes in the oxidation state, oxidation number, to help balance equations. Should be able to notice that from the syllabus. This is a plus 5. Changes in oxidation number must be balanced. So I could see the LCM, the lowest common multiple, between 1 and 5. This is multiplied by 1, this is multiplied by 5. That's why I need this to be multiplied by 5. That's why I need 5 NaCl. I just need this multiplied by 1. I just have 1 of it, which I don't put a number in front. Now, the oxidation number has been balanced by that. Now it's just balancing the atoms. 5 sodium plus another sodium, it gives me 6 sodium. And then 5 chlorine plus 1 more chlorine is 6 chlorine atoms. So I need 3 CO2. I've got 6 hydrogens. No hydrogen, no hydrogen. So I need 3 water molecules to give me the 6 hydrogens. So obviously this is the equation that we are trying to balance here. It's not needed for this question, obviously, but it's important that you know how to balance it as part of the underlying theory, because you still have paper 2 and paper 3, I guess, paper 4 as well. So those are all theory papers that can test your ability to balance equations using changes in oxidation number. Question 36, so what do we have here? Question 36 is about melting point. Melting point, sodium, magnesium, aluminium. So, this is about metals. We have giant metallic structure, giant metallic lattice structure. Of course, you know that in a giant metallic lattice structure, this is what you have, the cations, because the metal delocalizes the valence electrons. These are the C of valence electrons. A lot of students, when they remember this, they just remember C of electrons. Technically speaking, it's actually valence electrons, because the metal cations is formed as a result of the metal atoms losing only the outermost shell electrons. We have a force of attraction between something negative and something positive. So when we want to melt or boil metals, we need to break strong metallic bonds. What is metallic bond? Metallic bond was defined in your bonding topic as the electrostatic force of attraction between these positively charged cations and the sea of delocalized valence electrons. So how are you going to justify or quantify the strength of attraction between the positive ions and the negative charge of the electrons? There are a couple of factors. So there are factors for the strength of metallic bonds. This is actually a metallic bond topic. One of which is obviously if your number of electrons, if your number of valence electrons delocalize increases, then metallic bond gets stronger, and therefore melting point will get higher, because if you have more electrons in the system, there's more attractions, harder to break the metallic bonds, which gets stronger, and therefore melting point increases. The other factors you should be thinking about, there's nothing else I can talk about the electrons because electrons don't have sizes, but the cations has sizes. The cations also have charges. So I'm talking about the charge on the cation. So charge of cations increases, so metallic bond will become stronger as well. And last but not least, the size. So the size of the cation increases, then the metallic bond will get weaker, because if you think about the attraction is actually from the nucleus, which I have positive charge. The net positive charge is in the nucleus and is attracted to the electrons. So the bigger the size, the further away is the negative charge from the nucleus in the center, and therefore the metallic bond is slightly weaker. Going back to sodium, magnesium, aluminium, so we should be able to see a trend there from sodium to magnesium to aluminium. So number of valence electron 1, 2 and 3, and then you will get Na plus, Mg2 plus, Al3 plus. If you think about the ionic radius, so Na plus is actually bigger than Mg2 plus, is actually bigger than Al3 plus. So if you spot all of these, you should be able to see factor number 1. So this is factor number 1, and it's not statement number 1, it's factor number 1, but I haven't really gone through the option yet. So this is factor 1 above, and that is statement number 2. Statement number 2, there are more delocalized electrons per metal ions, because if you form this, then you will have 3 delocalized electrons per ions. So statement number 2 is actually correct. It's actually statement number 1 from, it's factor number 1 from what I have said above, okay? Or maybe I can just change the factor a little bit, okay? Because it looks confusing now. All right, factor 2 above. Anyway, and then the number 1, charge of the metal cations, so that is just number 1. Charge of the metal cations, so that is factor number 1 above, so that is statement 1 correct as well. Okay, and then the other one is the radius of the metal ion decreases, so the cation getting smaller and smaller. You can get this from the data booklet as well, but obviously you need to know the trend, because size of the atom decreases. This is atomic radius, and then the cation is smaller than the parent atom, but the cation is also getting smaller and smaller as you go from sodium ion to the aluminium ions, and the same thing goes for the anion. So these are the ionic radius, these are the atomic radius. These are very popular multiple choice questions which they could ask in the theory paper as well. Okay, so that is factor number 3. Factor 3, statement 3 is definitely correct, and therefore 1, 2 and 3 are correct. We are looking at all 3 of them are correct. Okay, question 37. I remember this question brought me a wrong answer previously, which I had to change slightly. What I mean is in the previous paper. Okay, it's actually got to do with symmetry, so let me just try and draw it the best I can. Not the best drawer in the world, but I love skeletal formula, so it's the most elegant thing I could think of, and if I draw it quite nicely, you can hopefully see what I'm trying to portray here. Hope you can see that there's a symmetry. There's a symmetry if I think about the middle point here. So my diagram is not the best in the world, but there's like symmetry in between there. And where can I see the symmetry? let me see, how am I going to relate it? If I put this 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, I could rotate the molecule about 120 degree. So you can obviously see 1, 2, and 3 like that. And what's the best thing I could do? Like that, there's one plane, and another plane will be, it's basically in between that. No, that doesn't work out. All right, where is it? How do I, it's basically like you have 2 carbon there and you have 2 carbon there. The plane of symmetry is like that, in between that and in between that. Now another one will be, where is that? There. And another one will be, okay, by right they should all pass through the middle point there, okay, but my diagram is not the best. You can try on the diagram on your own paper. Anyway, the first bit is I'll check number 2. So this is actually the easier bit because they're asking a molecular formula. The definition of molecular formula is a year 9 concept. I know it because I have just taught a year 9 the definition of molecular formula. It is the actual number of atoms in one single molecule. In one single molecule, how many actual atoms are there? There are 12 carbons. For each of these, 11 and 12, 8 and 9, 3 and 4, there are 2 hydrogens, so 2 times 6 is 12, and then for each of these there's 1 and 1, so 12 plus 2 is 14, 16, and 18. Am I correct? I might have done a mistake. Did I make a mistake? So let's have a look again. Let's just double check this. Okay, let me just copy paste that and I will work on this diagram. Nope, that doesn't look all right. Okay, I'm just trying to remove all these fragment lines so that it become easier for me to show what I want to show. Okay, that is probably as good as I can get it to be without drawing the whole thing again. So there's Br there and Br there. So let's try and count the carbon, the hydrogen, okay? So 1, 2, 3 and 4, 5 and 6. I should probably use a different color. So the blue one represents 1 hydrogen, okay? So there is 6 already. And then if I use a pink one, where is it? Okay, if I use a pink one, there will be 2, 4, 6, 8, 10, 12. So 12 plus 6 of that blue one, there's going to be 18 hydrogen. 18 hydrogen, C12H18, Br6, and not as given, C12H20, Br6. So obviously number 2 is going to be wrong. If number 2 is wrong, that means only 1 is correct. That is option D there. Okay, so I hope that makes sense there. Let me just double check. 2, 4, 6, 8, 10, 12, 14, 16, 18. Yep, that's what I got. And they say each brominated carbon atom is chiral. So each brominated carbon atom there, the blue one I have highlighted. So it's 1 group, 2 group, 3 groups, and 1 hydrogen. Okay, so it's obviously chiral because this group here has got 2 bromines, this group here has got 3 bromines, so this group and this group is different. There's 1 hydrogen which is not shown in the skeletal formula, so each brominated carbon is chiral. And they say the carbon bond angle are all 120 degree. That is absolutely wrong. All the carbon are 109 degree, because just because they don't show you the hydrogen doesn't mean it's not there. So the 4 bond pair repel equally. This is going to be your classic tetrahedral. And you should also know hybridization is all carbon sp3 hybridizations, and there is 109 degree or 109.5 tetrahedral geometry. Question 38. So this is different type of reactions of bromoethane. So this is bromoethane, and when you react it with just water, when you react it with NaOH in water, Okay, NaOH in water. This is NaOH in ethanol. And this is NaOH in water. Okay, now this is what they say. This is aqueous because it's in water. This is in ethanol, so it's not aqueous. Bromoethane, well, we know that NaOH in ethanol is going to favor elimination. So this one favor elimination, whereas NaOH in H2O, that favor hydrolysis. Hydrolysis basically is breaking the CBr, so CBr become COH. So looking at that, I would imagine that should give me that, and well, actually they give me the product, to be honest. So they said this is ethene. There's option 2, this is option 3, and in option 1 they say it will give me ethane 1,2-diol, and that is not going to be right because you only started with one bromine. If you started with bromine and bromine there, 1,2-dibromo, you will get this upon hydrolysis, but you only have one CBr, so you only hydrolyze one of the CBr and you get COH alcohol. So 2 and 3 are correct because 2 is part of the elimination product. You actually you actually kick out HBr like that. So there's elimination. So 2 and 3 are correct. That is going to be option C. Okay. Question 39. What do we have? We have X. Let me just draw X. C2H5 and then COCH3. Skeletal formula is beautiful and elegant, so you should really try and draw and convert everything to skeletal, and then it's much easier because you can always check CH3CH2, C2H5, COCH3, CH3CH2, which is the C2H5 and CHO, CH3CO2H, carboxylic acid. This is actually ethanoic acid. Not that they're asking for the name here. This is a 3-carbonaldehyde, so it's propanol. This is a butanol, and doesn't matter, butane 2 on, butane 3 on, there's only one isomer of it, so we'll always just call it butanol instead of butane 2 on, okay, which is also correct, of course. Now they say Tollens reagent, so I'm just looking at statement number 2. Tollens reagent can only oxidize aldehyde, so we're looking just for aldehyde, and our aldehyde is our propanol. So Y reacts with Tollens, not that and not that. So number 2 is correct. Okay. Don't know. Did that come out alright? Yep, that came out alright. And what else? X reacts with alkaline aqueous iodine. So alkaline aqueous iodine come out in 2 places. This is for the iodoform test. Iodoform test is not just for carbonyl. It's also CH3CHOH and CH3CO. So it also come up in your alcohol topic. None of this is alcohol, so I guess we're just looking for the CH3CO. So the CH3CO should be very obvious. You have CH3CO. You do not have CH3CO. You have a CH3CO here, but it will not work on this acid because you have an alkaline condition. It will in fact, first of all, just form the salt, and that will affect the chemistry a little bit. So it does not work. This thing does not work on a carboxylic acid, even though it has got a CH3CO, because you're in alkaline condition. Think about alkaline. Think about carboxylic acid, so no reaction there. You will not get the iodoform. So you see a yellow precipitate. The yellow precipitate is iodoform. Iodoform is actually triiodomethane. Okay. Anyway, so there is a reaction X with aqueous iodine. So that means statement 1 is also correct there. Okay. Last but not least, we are looking at, well, actually Z. I already mentioned that this alkaline aqueous iodine, the iodoform test does not work on this. So that is actually correct. So statement 3 is correct based on what I have said. So 1, 2, and 3 are correct. So therefore, option A is the best answer there. Question 40, we finally reached the end of this paper 1. Fairly long paper, obviously. I always enjoy doing multiple choice, but they are usually pretty long. So question 40, what we have is a cyclic ester. So like that, cyclic because, well, it's not open chain, it's just cyclic. So there's 1, 2, 3, and 4, and 5 carbon. They say 5 hydroxy pentanoic acid. So hydroxy 1, 2, 3. Oops, they are giving the main priority to the carboxylic acid. So there's 1, 2, 3, 4, 5 hydroxy pentanoic acid. As you can imagine, the alcohol loses the H, the carboxylic acid loses the OH, and therefore when you form this cyclic ester, you will also kick out HOH, which is H2O. That is why this reaction is called condensation reaction. When you form an ester, when you form an amide, it's called a condensation reaction. It's the opposite of hydrolysis, which of course we don't just use water for hydrolysis, even though the equation says so. We use acidic conditions, we use alkaline condition. Those are the acid and base hydrolysis of esters, of amides, of nitriles, all in AS chemistry. So option 2 is definitely correct. You say number 1, it say it use acidified dichromate 6. Dichromate 6 is an oxidizing agent, and we are not doing redox here, we are doing condensation. So it is a condensation reaction, not a redox reaction. So therefore 1 is incorrect. 2 is correct, 1 is incorrect. Therefore we're looking at 2 and 3 are correct. So that's option C then. Okay, and finally obviously 3, that is a reaction can be catalyzed by using concentrated H2SO4. That is in fact our condition to form ester in AS chemistry as part of that condensation. The reason why we use consulfuric acid is actually these things are reversible, and we use that as a catalyst to try and dehydrate. So this is a dehydrating agent, and they will help to remove the water. And when you remove the water, the concentration of water goes down, the equilibrium will be pushed further to increase the yield of that product. But on the other hand, this is also a strong acid, and you will also be a catalyst. All right, so it's an acid catalyst in this reaction, but it also acts as a dehydrating agent, which of course you use consulfuric acid as well in your alcohol topic. Okay, so we've reached the end of this tutorial, and I hope they have been useful. If it had, don't forget to check out the various other playlists on my channel. They should all be in one link, which I've shared across throughout the channel. And these document links provide you further links to all the various playlists and make it easier to navigate through my channel. Okay, so don't forget to subscribe to the channel, click the button on the bottom right, as easy as that, and turn your notifications on to receive to receive notifications. And thank you for watching. Do follow me at ptet.chemistry, ptet.chemistry on Facebook, Instagram, Twitter, and Telegram. And yeah, leave any comments, likes, get in touch, whatever. All right, let me know if you spot any mistakes. Yeah, thank you for watching again.